Hello everyone. In this lab, we will implement OFDM physical layer on RFSoC board. For this, we have used a GitHub based model for the physical layer implementation, and the design is created entirely as Simulink models, which are used to generate various hardware based IPs as transmitter, receiver, and interpolate and decimate, which we will see in the subsequent videos. So first, we will launch the system generator tool to access the Simulink models. So once the system generator tool is launched, navigate to the directory where the downloaded GitHub repository is found. So it will be of the name RFSoC OFDM underscore main. So in this directory, we have first the boards folder in which we have the IP folder. Go to the final models directory. Here all the Simulink models are present. So first we will add this directory to the path to the MATLAB path. So these are the various Simulink models provided here for the internal blocks that are being used for the receivers and the transmitters. The variables folder contains all the preamble and pilot and the cyclic prefix values which will be used for the design internally. Then we have the scripts folder in which we have the filter setup file which we will explain later, and the 512 QAM and 1024 QAM modulation values. So first we will open the OFDM RX hardware. This will open two MATLAB windows. One is the magnetic response of the various filters and combination of filters used, and next is the Simulink model. So for the basic overview of this entire Simulink model, first we have the PS part which provides the modulation scheme and the enable signal to the transmitter block in the PL. The transmitter block then computes the data symbols and the transmitted values, which contains the preamble, pilot, and data symbols, which are then passed to the interpolate block. Interpolate block then upconverts the data to a desired carrier frequency by a series of FIR filters. This upconverted data is then passed to the channel block. Through the channel and the ADC, the data is then passed to the decimate block again in the PL, which decimates the data back to the baseband and passes it to the last receiver block. The receiver block then computes the channel estimation values and the recovered complex data symbols. These values are then finally passed to the PS for plotting purposes. In all the Simulink models, the red blocks are used to generate the IPs via the system generator tool, and the highlighted blue blocks are used to generate the IPs via the HDL coder tool. Similarly, open the transmitter Simulink model. So this Simulink model is just same as the receiver model, only the difference is that this will be used to generate the transmitter block and the interpolate block. The transmitter block will be again generated by using the HDL coder, and the interpolate block will be generated by using the system generator tool. So first we'll understand how the interpolation is done here. So here we use a series of FIR filters to upconvert the data from 1 MHz to any desired carrier frequency. So in the given example, the data is first converted by a factor of 2 by using two half-band filters for the imaginary and real part separately, which gives us 2 MHz as a sample rate. Then the data is further interpolated by a factor of 2 by using two CIC compensation filters, giving us the data at 4 MHz. Then the data is further interpolated by a factor of 48 by using CIC interpolation filters. Then at the last, two SSR filters are used to further interpolate the data by a factor of 2. So SSR means that my data sample rate can be achieved as 384 MHz while maintaining the sampling clock as 192 MHz. This is done by concatenating two data symbols in time frame as one data block. So here it can be seen that the imaginary values and the real values, that is I0, I1 and imaginary values Q0, Q1 of two adjacent data values adjacent in time frame are concatenated as a single data block and are further passed as output. Similarly, in the decimate block of the OFDM receiver model, The data here is received at the sample rate of 384 megahertz and then further decimated to 1 megahertz by using a series of FIR filters. These FIR filters are the same as the ones which were used in the interpolation block, that is the SSR filters, CIC decimation filter, CIC compensation filter, and then finally the half band filter. Only the difference is that they are used for decimation and are used in opposite order of the interpolation ones. So here the input data is at 384 megahertz and the imaginary and the real values of the two data symbols which were concatenated earlier are separated and then further passed to the half band SSR filter blocks, and then by series of decimation the data is down converted to 1 megahertz here and then up sampled to 12 megahertz before passing to the receiver block. So now we will see how to generate, interpolate and decimate IPs using the system generator tool. Additionally, we will generate these IP blocks for carrier frequency of 240 MHz. So for that, first we will move to filter setup file and update the filter coefficients accordingly. So here are the rates of the interpolation and decimation filters defined. So for 240, we will choose these factors to be 2, 6 and 20 rather than 2 and 48. Here are the output frequencies of all the filters defined. Then we will need to update these interpolation factors while generating the filter coefficients as well. So here is for the CIC compensation filter, and here we are interpolating by factor of 6. Then here starts the decimation part. So here it is defined the decimation factor of the first CIC filter, which is 20 rather than 48. And here is the output frequency of the first CIC filter. So it receives the input sample rate at 384 megahertz, which will be 240 now, and the output would be 240 divided by the decimation rate, which we defined as 20 here. Second, the second CIC compensation filter will also be decimating by a factor of 6 rather than 2. So since we are not using SSR in this case, we are only interpolating by factor of 2, 6 and 20. We will remove the part which corresponds to the SSR filters also. So here we are plotting the magnitude response of all the filters combined. Now since there is no SSR filter, this will be only for the half band and CIC filters. Let's check if anything is left. Okay. Now we'll save these changes in the filter setup file, and then now we need to change the corresponding factors in the decimation and interpolate blocks also. So first we need to remove these SSR filters from the decimate block, and these can be entirely cropped out. Okay. And since it's only one data block being received at a time, we don't need to separate the interpolate we don't need to separate the imaginary part of two data blocks which were concatenated in the original case. 0 to 50. So this is for the later part. These were the outputs of the SSR filters, and the valid signal can be made as external port here since it is not required as input. Terminator. So next we need to update the factors of these blocks also. So the first CIC decimation filter takes its factor from the filter setup file itself, and the second we need to update. So here it is 6 for the imaginary and for the real part. And half band filter will always decimate by a factor of 2. And similar changes we need to make in the interpolate diagram. Half band, if this one is interpolating by a factor of 6, and we don't need the SSR part. And we don't need the concatenate block also. So the real and imaginary parts will be passed as it is to the concatenate block, which is, I have inputs 2, and the data is 240 megahertz. So my valid signal will also be sampled for 240. Once it is done, in the channel block also we are receiving only one data block at a time. So we will remove the part for the second data value. So yes, okay, and only the real part will be going as output here. So once these changes are done, we can verify whether the interpolation and decimation is done by the required factors. So for that, first we will run the filter setup file to generate the new values. So we'll clear the old values, old variables, and run this file. So here we can see that the interpolation is done by factor of 1 to 2, then by factor of 6 to receive 12 megahertz, and then finally by factor of 20 to generate 240 megahertz. So here we can use the sample time display to display the sample rate of all these transactions in a color coded manner. But before that, in the decimate block, as we saw earlier that there were input gateways, hardware compatible input gateways for data and valid blocks, and they are sampled by uh, so these So these need to be sampled correctly for the incoming data of 240 megahertz rather than the original case. So this will be one, and this is FCIC. This need to be done for all these gateways. 1 by FCIC, and the number of input bits is 16 rather than 32 because there is no concatenation of two real and imaginary values. So now we can display. So we can display in the terms of frequency, and here we see that this incoming data is for 12, which is first downsampled to 1 megahertz, then interpolated to 2 megahertz, then 12 megahertz, and then finally 240 megahertz. And then in decimate, the incoming data is at 240 megahertz, which is downsampled to 12, and then 2 megahertz, and then finally to 12 megahertz before passing to receiver block. So once this is verified, we can now generate the decimate IP using the system generator tool. So we'll just add a new block to see all the settings. System generator. So first we'll specify the board, which is ZCU111, and we will define the directory where I need my IP to be created. So here I'll create a new directory outside in the IP folder itself as generated. So this one is decimate RX. So this will be the location of the new IP created. And for clocking, the FPGA clock period would be 240 megahertz. So that would be 1000 by 240 nanoseconds. And in the simulink system period, which is same as the simulink clock, which is used for the simulation purposes only, and it will be 1 by 240 e raised to power 6 as it is in seconds. And now we will generate the IP. So before generation, the design is compiled to check for any data rate errors or for any connection mismatches. Once that is done, the IP will be generated. So once the generation is completed, since this same Simulink model is used to generate the receiver model also, so our receiver IP is generated using the HDL coder tool rather than the system generator. So we can right click on it and open the HDL workflow advisor. So once this HDL workflow advisor is launched, we can start with the IP generation. So in this, we will say that the target workflow would be IP core generation to generate the hardware IP for Vivado, and the board is the ZCU111, and the project folder also we can decide here, which is in the regenerated. This is just OFDM RX. So this will be the location of receiver IP. So once the settings are made, we can run this task. So once this task is passed, for the target interface, this is the channel estimation, and this is the recovered complex data symbols, and this is the input data which this IP is receiving from the decimate. So all these are to be set as external ports, which can be later clubbed as a stream port in the Vivado that we'll see later. So once these are done, we can run this task. So once this task is passed, we'll move on to the next step. So here the design is checked at various levels, whether it is mappable to hardware or not. So we can run all these steps together. So when these tests are also passed, we can finally go for the IP generation. Here we just set the So here we define various settings for the IP generation, that includes its language and any optimization of operation like pipelining and all. And here for the clock settings, whether asynchronous and active high, active low. So we don't need to change these. And for the IP generation, the IP name will be OFTM RX and the version will be set as 0.4. So once this is done, we can again run all the steps together. Once the IP is generated, the IP report window will be displayed containing all its information like name and the ports and the optimization settings set. So after that, we close this workflow advisor. Now similar changes are to be made for the transmitter block also to generate the interpolate and the transmitter IPs. So for the interpolate block, the filter setup file need not be changed because all the values are already defined as per the factors required for 240 megahertz. Now going to the interpolate block in the transmitter simulating model. So as for the interpolate block, the filter setup file will remain same because the interpolation factors were already defined. So here in the simulating model, first we will remove these SSR filters, and then the CIC interpolation factors need to be redefined in these blocks. Then additionally, the interpolate block sends output after every stage of interpolation to the PS for plotting. So these data values are again to be interpolated to correct vector 240 megahertz before sending it to the PS. So these changes need to be made for the interpolation here. So first we will remove these SSR filters, and this imaginary and the concatenation will only have two inputs for the real and imaginary of one data value. So this real part will be passed as the lower bits and the imaginary part will be passed as the higher bits. Then the valid signals for the real and imaginary values are passed to the AND operation to send as collective valid output of the entire interpolate block. Now the interpolation output is of only 32 bits rather than 64. Next, this CIC interpolation is by factor of 6. And this CIC picks its interpolation factor from filter setup file itself. Then these interpolation, so after the half band, the interpolation is done by a factor of 2, giving us a sample rate of 2 megahertz. So it needs to be upsampled by 120 to give 240 megahertz at the output for the data values and the valid signals. Similarly, after the first CIC compensation filter, the interpolation is done by a factor of 6 to give 12 megahertz. So this needs to be interpolated by a factor of 20 to give 240 megahertz. So once these changes are done, we need to change the channel block also, as was done in the receiver model. Similarly, for the decimate block, the data is of only 16 bits. And the decimation, there is no SSR filter, so it is 240 megahertz at the input. And this CIC compensation, it still decimates by 6. So once these changes are done, we need to change the system generator block also to generate IP corresponding to 240 megahertz. So the board part selected is ZCU111, and the target directory can be set accordingly. Interpolate TX. And the clocking will be same as it was in the receiver block. 240 megahertz for the FPGA clock, and this signaling period will also be 240 megahertz. That is 1 by 240 e raised to power 6 seconds. So now we can use the sample time display to check for the data sample rate conversions. So we'll use the frequency display here. So here we can see that the data is coming at 12 megahertz, and in the interpolation it is after the first half band filter it is taken to 2 megahertz, then after CIC compensation it's 12 megahertz, and then after that final CIC interpolation it is up converted to 240 megahertz. So once this is correctly done, we can now generate the interpolate IP from the system generator. So just double click the system generator tool and select generate. Once the generation is completed, we can close this dialog box, and now we'll generate the transmitter IP. So this will be generated using the HDL workflow advisor. So once the HDL workflow advisor is set, we will again set the project folder and the target workflow as IP code generation. This was the very same process as it was in generating the receiver model. For the target interface, so here these modulation scheme and enable signals are very small data values that are passed only once to the transmitter block. So these will be set as AXI light, and the remaining will be again set as external port, which will be later declared as AXI stream interface. So for the HTML code generation, so here again the design will be checked for any errors while mapping it to hardware. So we can run all these checks all together. And for the HTML code generation, here the language and optimization options like pipelining and the clock options like synchronous and active, high, active, low are set. And this here finally the IP is generated with the name OFTMTX and version number 0.2. So we can run all these tasks together again. So once the IP is generated without any failure, the IP generation report dialog box will open containing all the settings that we made here in the workflow advisor. So we can simply close this and close this workflow advisor as well. So now we have generated all the IPs for the transmitter block, interpolate, decimate, and receiver. So next step is to integrate these IPs in the Vivado IP integrator. So that we'll see in the next video.